All right, so let's get started. I think I have 11:10 on my clock now. So it is my pleasure to introduce our guest speaker, Amir Gholami. He is a postdoc working in the Bear Lab, working with Professor Kurt Koitzer. He obtained his PhD from UT Austin, working with Professor George Biros. And he is also a winner of the Best Student Paper prize at Supercomputing 2017, and also a finalist for a Best Student Paper at Supercomputing 2014. So with that said, take it away, Amir.
Many thanks, Aditya, for the nice introduction. It's great to be here. This is the second lens that I'm seeing this class. Before, I was seeing it from miles away from the webcast, and it was very helpful for me to do my projects, and I got very interesting ideas from the class. So I hope this is my time to share what I know about GPUs, and I hope that it would be helpful. So this is the outline. I'm going to start to talk about what's the difference between CPU and GPU and what's the mindset behind using GPUs, which really boils down to throughput versus latency. And then we'll take a small, maybe introductory paths from going from the hardware in CPU to GPU. How would you design a GPU if you knew that throughput is important? And then we'll get into CUDA and what's important for getting good performance out of a GPU code, and then we'll do a brief OpenCL comparison between CUDA and OpenCL, how you should program there. So this is really the slide that is CPU versus GPU. CPUs are optimized for latency, and GPUs are optimized for throughput. And essentially, you will see a lot of hardwares that are in between, that are domain-specific architectures. For example, for machine learning now, there are applications that fall in between, and people are designing hardwares specific to that. But on the very left extreme, you want very low latency as much as possible, and you put a lot of hardware and software things into the CPU to reduce that as much as possible. And on the right, you say latency is not important for me. I want more work to be done than one work being done fast. So essentially, that's the difference. But this was not always obvious. So now that things have been done, we look at it, we're like, okay, that's obvious. But it wasn't always like that. So does anybody know what this table represents? This is somewhere in Germany in a museum. Maybe take a guess. Yeah.
Moore's law?
Yeah, very good. This is the Moore's law, and back in the 2000s, we were still in a area that the Moore's law was like 20 months, 22 months, and people were really wouldn't buy it that this will be useful for general purpose compute. So you wouldn't go build a GPU for a general purpose compute. You would stick with the CPU, and you would say, okay, in 2 years' time, the CPU is going to get better. And then, unlike graphics, if you're doing computation, scientific computing, there is a lot of things that require some hardware that was not supported on the GPU. So putting time and money here for changing GPU so that you can program it for example, a BLAS routine was not an obvious thing. So that's why, at that time, many people didn't believe that this is the right way to go. Now, from 98 or early 2000 to now, we see that all the companies have somehow followed up on this idea, including Intel. And they now have processors that are optimized for throughput. So for example, for Intel, you see in the blue, I'm showing the Intel server CPUs. So sometimes you see people compare GPUs with desktop CPUs or laptop CPUs. You have to always be aware, like they show 100x speed up. You really have to compare apples to apples. So if you want to compare a GPU, you have to compare it, for example, with a server CPU. So on the blue curve, you see the server CPUs on Intel, and then recently Intel started their own GPUs called Xeon Phis, and they have a next generation Knights Corner, KNL, and now Knights Mill. And on the green curve, you see the NVIDIA GPUs, and on the red is the AMD. So you see now we're getting a lot of peak performance out of GPUs, and these actually can be used for general purpose compute. But things, again, for the latency side, one other reason this has happened is that on the latency part, it's been really difficult to scale it. So there is this article by Dr. David Patterson that is a very interesting article where he shows how latency has scaled in the past years and how bandwidth has scaled. So you see that bandwidth, we have a lot more achievements on the bandwidth side compared to the latency. And he has this interesting quote that he says, the reason we cannot solve latency is because we cannot change the speed of light, because we cannot bribe God. So this is a very interesting article. Only if you're David Patterson, you can write an article like that. But it's true, and he also argues that for marketing, you can sell processors that have higher bandwidth, and people look for that. Usually people don't look for low latency. Like if you say 10 nanosecond, people don't buy that. But if you say I have an Ethernet that is 100 gigabyte per second, they're like, oh, irrespective of whether that's a good thing or a bad thing. So this is from a high level. This is how GPUs look like. So GPUs were there for graphics. And a GPU has had shader cores that would compute vectors, shapes in 3D for your graphics application. And had many of them, because you wanted, you had a big screen, embarrassingly parallel algorithm. And then it has, on the right, it has some texture memory. That's a specific memory for reading images and then performing filtering on it or performing interpolation, hardware accelerated. And then on the right, you had a lot of hardware for actually transferring this information to pixels that you see on your screen. So for example, you have the input, reading the data, and then the rasterizer that would get essentially this vector representation of graphics, and it would turn it into color map, bit maps, RGB maps. And then you had a work distributor that would essentially help managing. You have so many shader cores, how can I effectively manage that? And so they had a specific hardware there so that you can get as much performance out of the hardware as possible. Now that's expensive. And these, if you're doing compute, if you're multiplying matrices, you probably don't need a rasterizer. Now on the CPU side, again, the goal of Intel and AMD was to reduce latency as much as possible. So that's the idea behind their hardware. So a typical CPU architecture, it has a fetcher or decoder, which is essentially when you write an addition, it decodes that addition into a language understandable by the ALU so that it can perform the addition in binary. So that's what the fetcher and decoder does. Then you have the ALU itself. It's a bunch of multiplier and adder secrets. And then you have an execution context. You have the, for example, you need to know the thread state. Every thread has some registers, and then you need to know whether it's in a running state, whether it's stopped, or whether it's blocked, etc. And then on the right, you have a lot of hours and hours of research and development for increasing latency performance. So you have out-of-order execution. You have a lot of branch predictors, so that you don't have to wait for the if conditional to see what data you have to load. So you can predict it, so you can do stuff before that value is known. You have a lot of fancy prefetchers for memory. And you have very, very expensive data cache. So the cache hierarchy on the CPU is really good. The registers, sometimes you see people compare and say, a GPU has a lot more registers than a CPU, and then they would say, they would throw numbers. But you have to know that the register on a GPU is not the same quality register as on the CPU. So there is a very big cache, highly optimized, years of work. Now, we don't care about latency. So how can we get this architecture and go to a throughput optimized architecture? So first, let's get rid of all of the prefetching, all of the cache, expensive cache. Let's remove all of that. So I will have an ALU. I'll have one fetcher decoder and an execution context. Now I can put many of these together. So now I've saved some space, and I'll put as many as possible on my chip. So let's consider a 16 array of them. So on here, I have 16 fetcher and decoder, 16 ALUs, 16 different contexts. What else can I remove? Well, when you have, for example, let's take graphics. So on the left, I'm showing 16 pixels, and I want to compute the RGB map. So I have some input information, and I want to compute what's going to be the RGB values for each pixel. So you can imagine that many of these will be performing the same instructions. So I can actually share the fetcher and decoder for many of these ALUs. So that was the next idea. So if I look at the code, for example, for computing the bitmap, I can see that many of the instructions are the same. So why bother putting individual private fetcher and decoder for all of these ALUs? I can instead go and put one, and all of these ALUs will share the same fetcher and decoder. But that comes with an important restriction, that all of these ALUs have to perform the same instruction at the same cycle. So this is at that expense, and this is the most important thing you should know about CUDA program, that one of these units can execute the same instruction at an instance. So that was the big idea, and NVIDIA coined the term SIMT, single instruction, multiple threads. So I will have multiple threads coming to this ALU, and they will perform the same instruction. I can have multiple data. So for example, I want to rasterize an image. I will read in different data, but I will perform same addition, same multiplication for all of these data. So that was the next big idea. Now, as I said, this comes with a cost. So if I have an if condition here, so assume I'm looking at those 8 ALUs, and I have 8 threads, and they all come, there's no problem up to here. They're all executing the same code, same instruction. But then I have an if condition here, that if x is positive, do something, otherwise do another thing. Well, many of these threads may not, some of them may want to execute this part, the other parts may want to execute this statement. But because of the limitation of the hardware, I have to execute the same instruction. So what the hardware does for you is it says, okay, the first 2 and the 4th thread are true, so they will execute the yellow part, and everybody else will stay, they won't do any useful work. And then they would stay silent, and the other cores will perform this else condition. And then once they're done, they will rejoin. And in the worst case, the performance will be 1/8. If you have an 8-way thread divergence, you will get 1/8 of the performance. Which is a problem if you're not careful. So this is very important. If you're writing a CUDA code, you have to make sure that even if an algorithm is not optimal, but it has less thread divergence, you will probably get better performance. So the way I looked at this, when I first got this idea, I was like very confused, and then I was in Dr. Pengala's class, and he used the notion of Siamese twins. That really helped me. Think of these 8 threads as being completely connected to each other. They cannot go to different places. So one of them, if it wants to go to some place, everybody has to go. So that's essentially it's completely serial in that sense, if they want to do different things. Now, what if they hit a cache miss? What happens if I need to run my program on a data and I don't have the data? What idea would you do to hide that overhead? Does anybody have a guess?
Switch.
Yeah, exactly. So I can switch. So I can have many threads in my hardware, and I can say, okay, let the first 8 Siamese twins, which they call it as a warp, let's have the first group, the first warp, perform its unit of execution until it reaches a state that it, for example, wants some data, and that data is not available. Well, no problem. Tell the hardware to bring this data to this execution unit, but I switch to the next group that has a work ready. So then I can actually hide stalls very efficiently. So the first group performs execution, does vector addition, et cetera, until it reaches a stall. It needs some data that's not in the cache. Well, no problem. The hardware will immediately, with very low cost, and that's a unique thing about GPUs, with very low overhead, it immediately switches to the next group until the data that was required for the first group is ready. So you won't get good latency because the first task won't get finished, but you will get throughput. And so that's essentially the dilemma between CPU and GPU. And the magic is that you can switch within 1 to 2 cycles to the next group. So they have put a lot of hardware, a lot of effort to make sure that that switch is as fast as possible. So from the architecture part, I would say the summary is this. You use many slimmed down cores. They're not as powerful as the CPU cores that you see. And you pack as many ALUs as you can on the chip. And so if you look at the chip, actually it's a very, very large area compared to CPUs. And then you try to avoid the stalls by interleaving the execution with many warps. And when one group stalls, you switch to the other one. And you make sure that that switch is fast. As a programmer, that's transparent to you. You don't have to worry about that, and that's taken care of by the software, by the hardware, sorry. So again, different goals produce different designs. It wasn't like Intel didn't know about this. You know, this was very well known by the people in the architecture, but then they were targeting different domains. Latency cores, the workload is mainly it's designed for sequential tasks, and you put a lot of expensive things, out of order execution, register renaming, branch prediction, a lot of fancy prefetcher to make sure that latency is optimized. On the GPU side, forget about latency, it's about throughput, and so you assume that you have a lot of data and you want to perform the same computations on them, so you design your hardware so that you can be optimal for throughput. Well, Intel Intel and AMD, the CPU part also kind of took note and actually used this idea. I don't know who was first, but this notion of single instruction, multiple data is on the CPUs as well, and I think it's either covered in the class or will be covered at some point, where you can say, okay, I'm on the CPU side, I can also do the same thing. Maybe I'm adding a vector. I don't have to add them one by one. I can put a vector unit there that will add multiple floats or multiple integers. So this idea is there too, but there is a solid problem here that if you look at the past 10 years, you know, this was, I think, around 90s where there was the SSE standard where you could do 4 32-bit floating point addition or multiplication. But then as later CPU generation came, you had to change your code. So you couldn't execute the same code and get the same performance. So you had to actually, and you know, when I was doing my project, I had like if conditions, okay, if only SSE2 is available, use this code. And then when, you know, I wanted to write for the latest AVX512, I had to rethink all of it. How do I optimally execute this, write a brand new code for this? But on the GPU side, that's not important. You write the same code, and the same code will perform very well on the new architecture. It wouldn't be, at least it wouldn't be unrunnable on the new architecture. You can still run SSE on AVX512, but you will get very bad performance. And that's the thing here. If you don't use SIMD right now, there is no way of getting anywhere near the peak. So when they compute the peak, actually, they consider that you can use that completely. You know, you can saturate that. Now, for the single instruction multiple threads, there's a little subtlety between SIMD and SIMT. People usually use it interchangeably, but the subtle differences is that in SIMT, that's the GPU, every thread has its own register set, and they can possibly execute different paths. As we saw, you can have an if condition, some of them execute certain instructions, the other ones execute certain other instructions. You can still do some hacks to allow that to happen on the SIMD, but it's not as, you know, as straightforward as in the SIMT case. And then Intel has this simultaneous multi-threading, hyper-threading as well there, which I think will be covered at a later time in the class. So essentially, the only con that I can say about SIMT, which you need to be aware of, is this notion of thread divergence. So the idea is that all of these, this is again a Siamese twin, a warp, a bunch of threads reading different data, performing the same instruction, multiplication or addition. The only problem is that they can diverge. So if I reach a if condition, I have to stall the other threads until these finish their work, and then I execute the other one. So that's essentially the only problem with the SIMT, the most important problem with the SIMT that you need to be aware of. So here, you know, I have to wait, then there's some instructions to reconverge them, and then everybody performs Z, which doesn't have an if condition. All right, so now let's get to the CUDA programming model. So CUDA is a very, you know, nice product that came out of Stanford. It was originally called Brook. Ian Buck, who was working with Bill Daly, you know, wrote a compiler called Brook, and he later joined NVIDIA in 2003 and started what's called CUDA. And then on the AMD side, CUDA is a proprietary compiler for NVIDIA. On the AMD side, there is OpenCL, which is actually a consortium between Apple, AMD, Qualcomm, that you can write code in OpenCL and run it on AMD software. And they're pretty close to each other. So the CUDA exposes a hierarchy of threads into, do you have a question? No. So CUDA exposes this hierarchy of threads in a notion of grids, blocks, and threads. So it's essentially a way to organize how threads are executed on your GPU. So a block, so let's say you have a matrix. So the easiest way to think about this is, I was very confused first. I had to really think about like why do they have it, and then how does it work in 3D, etc. But it's just a remapping. You don't have to think about it this way. But think you have a matrix or an image, and you want to run a code on this image. What the CUDA does for you is you can specify this grid, which threads on this image will execute where, and then every one of these grids will have a bunch of blocks. And every block will be executed by one of those blocks of ALUs. So each of these will be executed independent of the other blocks. And every block can have a bunch of threads. Again, it doesn't have to be this way. You can reorganize it the way you want. They just give you this possibility of using it in a 2D matrix-like fashion. And every thread has its own private register, private memory, and it can be mapped to 1D, 2D, or 3D. But this part is really not important. You can just think that it gives you, for example, 10 threads. So again, you can, you have your grid. You can have multiple kernels execute at the same time on the GPU, and a grid will have a bunch of blocks that will be executed back to back. And every one of these blocks will have, for example, 256 threads. You can think of it as 3D, you can think of it as 1D. It's just a matter of how you think about it. But it gives you like 200 threads to perform to do the execution. Is this clear?
All right, sir. I didn't quite catch up, but what's the difference of illustrating in 2D or 3D? Because I thought it's like a hardware implementation, so whether it's in 2D or 3D, it's all mapped to a physical location. So is it just for illustrating the concept? Okay.
Yeah, it's essentially, think about it as a 1D array. So if I have 200 threads, these are really 200 1D array. The hardware doesn't see anything 3D. It's just that if you're, for example, working with a tensor or a 3D image, it was easier for people, to think about it this way. And then the CUDA gives you, like, when you want to get the thread ID, it gives you the, X direction, Y direction, and Z direction. But again, you don't have to think about it this way. So in the beginning, what I did was not very comfortable with this in the very beginning. So I did like an array. I would say, give me 256 threads, and I will remap it to the application that I have. Sure. So what is a CUDA thread? It's an independent thread that can execute, but they're connected in a warp. So everybody has to execute the same instruction. That's the only limit. Has its own program counter, has its own variables, and there's a context memory that knows what's the state of this thread. Has it, a hidden cache miss? Is it running? Is it stale? And you don't have to take care of this. The hardware will take care of all of that. And CUDA threads may be physical threads or maybe virtual. So it may be actually a software thread. Again, these parts you don't have to really worry about. But the main thing is that you need to take care that, note that it's for data parallelism. So I have a lot of data, I load them. All of these threads will have different data loaded, but they will perform the same instruction for the most part on this data. And so there is data parallelism. You can, across the block, these threads can talk to each other, but not, in a block they can talk to each other, but not across a block. And you can also do task parallelism. But let's get a little bit, let me explain why you cannot do the among blocks in a few slides that will come up. So I have a kernel, I want to run a kernel, I'll need, let's say, 2,000 threads. So the CUDA will give me so many in a block. I have n threads in one block. And these will only live in this block. They cannot talk to another block. That's the main limit. And I can have, 2D, 3D IDs, but again, it really doesn't matter. So the CUDA will tell me, okay, this is thread number X, this is thread number Y, in 1D, 2D, or 3D. And the CUDA block is essentially, if you remember the picture we had earlier, let me see if I can bring it. So each of these units will perform the execution for one of the blocks, independent of the other one. I can run several kernels, completely different. So the block lives in this side of the drawing that we have here. So a thread block has a bunch of threads in it that are running in parallel, and all the blocks in a kernel have the same entry point, and they may execute any code they want. So any block can execute a different instruction set than the other block, but within the block they execute the same instruction. And a very important point is that when you write the code, you have to make sure that your program doesn't depend on which block is going to be executed first. You cannot do synchronization between blocks. So does anybody know a workaround? Like, can I ask every block to write something into the global memory, like an array of booleans, and then set it to 1, and I will check if all of them are 1, it's like a synchronization, right? Or maybe I can transfer data this way, because they're somehow connected. But there is a problem with this approach. Does anybody have a guess what that problem may be? Because you shouldn't make any assumption of the ordering of the block execution. And another problem is that your code may require a very large number of blocks that cannot be executed at the same time. So what the GPU does, it doesn't restrict you to request 2,000 blocks, but it cannot really run 2,000 blocks simultaneously. So what it does, it will do the first 200. Once the first 200 are finished, it will do the next 200, next 200. So if I do that trick, then there will be an immediate deadlock because the other blocks are not there at all. So that's what I thought. When I got this idea, I was like, well, that's easy. You can just do a global memory, write booleans, but it actually doesn't work. But they have changed it. So as of CUDA 9, they allow this, but you have to make sure, it's your responsibility to make sure that the number of blocks can actually run in the same time on the GPU. So you cannot use it for 2,000 blocks. Do you have a question? And that is only supported on Pascal and Volta, that they actually allow you, they give you some control that these many blocks are going to concurrently execute on the GPU, but those numbers could not exceed the maximum hardware limit. So that's essentially the whole idea. Don't do it though. It's not really it's not a really good solution, and it will be limited only to certain GPUs. And it's essentially best to avoid any synchronization between blocks. Within block you can do it, but across blocks you should assume that they're completely independent. All right, what's the structure of a CUDA program? It's really not a lot of code. It's a very clean, actually, way of writing code. If you read an OpenCL, it's a little bit messier. But the basic program is very simple. First, you allocate memory on the CPU. I have a bunch of arrays in the CPU, the usual thing. I do malloc or new. Then I have to allocate some memory on the GPU. If I want to transfer the data, I have to tell the driver that allocate this much of memory for me. So that's also simple. You allocate it on the GPU. Then I have to, of course, transfer the data. If I have an image, I have to transfer it to the GPU. So there is memcopy, very similar to CPU memcopy instructions. I copy the data to the GPU. Then there is a special way that I can call a function very similar to a C function that will execute on the GPU. And then, of course, I have to transfer it back to the CPU, which is, again, the memcopy. So it's pretty clean. And then I have to just clean up the memory. Very, very similar to a usual C code. So is this clear? All right. Now I have to, there is a compiler, and you can imagine that these are different architectures. I have a CPU x86 and I have a GPU. So they have to be compiled to different instructions. So how would you do that? You would, assign different functions with different names, and then the compiler will know that this kernel has to be compiled for GPU, the other kernels have to be compiled for the CPU. How do you do that? If you prepend device before a function name, it will be compiled for the device that you have, for the GPU. And if you have host, it will be only for the CPU. But the CPU has to call an entry function to the GPU, and that is essentially prepended by global, which means that the host can call this to start the GPU kernel. And the important thing here is that when you're calling a GPU kernel, you cannot get anything returned from that function. So that strictly has to be void. If you want anything returned, you can write it in a pointer and then transfer the data of the pointer. So from 1,000 miles, this is the global thing, the global prepending global to a function called kernel. It can only return void. It cannot return float. That will give you a compilation error. And then I can define my own way of how I want these threads to look like on this GPU. I can define a grid. I want 100 by 50 different blocks. So this is 5,000 different blocks that will be executed back to back on the GPU. And every block, I want it to have 256 threads. I could have just, written 256.1.1. That's up to me. And that's what I started with. So I can say every block, give me 256 threads. And I need these many blocks, 5,000 blocks. And this is how I will execute the kernel. You write kernel, and then 3 less than signs, and then you close it with greater than signs, and you give it the grid dimension and the block dimension. And there is a third option that I'll explain later. So let's take an example. I can have a grid. Each of these, again, is a block that will be executed on one of those execution units. And let me specify the block dimension to be 5, so every one of them will have only 5 threads. So these guys will execute on one of those execution units. They can talk to each other, but 0 and 1 cannot talk. So is this clear? All right. So the first program, let's do vector addition. So I have my main. I have an array of size n, and I want to add a and b. So if I had a CPU code, I would do a for loop. I would say, okay, for I from 0 to n, add a and b, and then store the result in C. So here instead, what I do, I say, call this global kernel, give it the grid dimension, and divide it by 256 grid. Every grid will have 256 threads. And every one of these threads will see these instructions. It will first get its index where it is in this array, and then it will add a and b, and it will store it in C. So that's essentially the code. And that will be performed on the GPU. Now, there is a problem here. Does anybody know what's the problem here? There's actually a couple of problems, but what strikes you the most when you see this? So will this be valid for any value of n?
No.
What happens if n is any number?
It'll index out of the ends of the array.
Can you say that again?
No, like index out of the array.
Yeah, exactly. It will either index out of the array, or actually it will index before the array is finished. Because if n is not a multiple of 256, this will give you smaller than n. So n divided by 256 will give you, for example, if it's 300, it will give you 1. So it will actually not add the last tail of the array. So there is actually a bug here. So let's fix that first. So I will assign this to be 0 of this n divided by 256. So if my array size is 300, I will ask it to give me two grids. But now, as you said, it's possible that I will have threads that have an ID larger than n. So I can simply put an if statement here and say if the index is less than n, do it, otherwise you just return. And this doesn't have an overhead because there is no branching here. Is this clear? All right. So of course, we have to copy the data. So let's see how that's done. I will first allocate the host array. There's usually a clean way of writing code for GPU where people prepend H for host array and prepend D for device array. So I will first allocate my device array. Then to allocate I will first allocate the host array. To allocate the device array, I have to call a function called CUDA-malloc. Very simple. It's exactly like malloc. And I give it the pointer address, and I give it how much memory I want to allocate. Size of float times n. And then, to transfer the data to the GPU, I have to use a memcopy instruction. Very similar to the usual memcopy in the CPU. You just prepend it with CUDA memcopy. You give it the device pointer, the host pointer, the number of bytes that you have to send, and then the direction. Is this host to device or device to host? Then I will call this vector addition kernel, and I will copy the data back, and I'm done. But there is another bug here. Does anybody know what's the last bug? There's actually 2 bugs. I have to clean up the memory. So I didn't free the memory. So I have to do CUDA free for the device, and I have to do free for my host array. And don't forget that. Usually there's a lot of bugs like that. So the key point, okay, so that was your first program. You can run that, and you will get some data back. But how do you write good codes that will be able to utilize all the powers that you have in the GPU? So it's the usual with requirements that you have to do locality. You have to make sure that you're accessing memory in a way that there is very few cache misses. And you have to, of course, have a lot of parallelism. There is a couple of things that are kind of unique to GPUs, which is memory bank conflicts that we'll cover, and making sure that there is no thread divergence. That's very, very important. Like when I worked for AMD, if I could see that if I put the smallest if condition there, the performance would tank completely. So make sure that you can avoid that as much as possible. So let's talk about the memory so that we can see what's this bank conflict, what's the problem with that. So every thread has its own private memory. It has to, read the data, perform some, calculations, store it in its memory. So there is per-thread local memory. That's fine. But then within a block, these threads have to somehow talk to each other, right? It will be very restrictive if you don't allow that. So I can put a scratchpad there and ask everybody to write or read data from it. It's shared memory. So everybody can write, everybody can read. And I will invest time and money so that this is fast. So if I want to access this is very fast, on-chip memory. Then there is global memory, that is off-chip. So that's, when you have like a Volta or Pascal that has 16 gigabyte memory, this is the off-chip memory. Accessing this memory is extremely expensive, and there is really no good hardware and no intention of speeding this up. That's what the CPUs do. There is a very, very expensive cache hierarchy to make sure that this access time is optimized. That's not the case on the GPU. So you have to take care of that. And then there is the host memory. You have your CPU, and this is how you do CUDA memcopy. It's connected via PCIe or NVLink that will allow you to transfer data to the GPU and back. All right, the first problem, you already talked about it. It's essentially the thread divergence. I guess you already know about this now, so let me skip this. Is this clear for everybody? Did everybody get this part? Second thing is synchronization. I mean, I cannot expect all the programs that I will be writing to be completely independent. That will restrict the GPU pretty much. You can't do any real good, useful work. So I can do synchronization. Synchronization within a block is expensive, but it's not crazy. But you have to try to avoid it if you really, really want to write very good code. But if you cannot avoid it, there is this function called sync threads, so that all the threads have to finish their execution, and until they reach here, everybody's at the same page. And then you can continue. So that's how you can do the synchronization. Now, I may want to run different kernels on the GPU. I have Volta, it has 80 cores, and I can run different kernels. Some of these kernels may depend on each other. So I may need to do synchronization and say, let kernel 1 finish, and then kernel 2 start. There is an implicit synchronization that is kind of important to know. Sometimes you know your algorithm is independent, but the compiler sees something. It sees that C was given here, and again, C is being used. Maybe you're just reading C here, and you want to override it here. So the compiler won't allow you to execute this before executing this guy. So note that there is an implicit barrier here that the compiler puts here. If you want to do it yourself, you can do device synchronize. And that will stop the next kernel. It will let the first kernel to finish, and then it will schedule, for example, vector dot on the GPU. All right, let's do the second example. Let's perform an array reduction. I have a matrix here, 4 by 4, and I want to just compute the sum of all the elements in this array. So there is a couple of ways we can do this. Does anybody want to, there is a lot of right ways to do this. So do people want to propose methods to do this on the GPU? The simplest way is to just get one thread and do a for loop, but that wouldn't be a very good solution. Sure.
You could have the threads sum neighboring elements and then do that kind of recursively until you've summed everything.
Can you explain how to do it on the recursive part?
Sure. So you sum neighboring elements and then you sum, I guess, 2 to the n neighboring elements repeatedly until you've done it log n times.
So that's a very good solution. It's essentially, this is a parallel. You can do a tree parallel, right? So you can sum the neighboring ones, then sum the next neighboring, and the next neighboring, and then sum the sums. That's essentially what we're going to do. So let's do that. Let's just look at a block. This lives on a block. I have 4 warps. Let's say I have 4 warps. I can ask the first warp to compute the sum of these 4 elements. As you said, what was your name?
Greg.
Greg. So as Greg said, I can take the first 4 elements. I can ask the first warp to sum them up, put it in a shared memory. Then the next warp, next warp, next warp, they can sum the elements. And then, once I have this data, I can ask one of these warps to perform another recursive operation on this 4-element array, and I will get the result. But is this a synchronization-free algorithm? Do I need any kind of synchronization?
You need to wait for the shared memory to fill up until you do the next.
Exactly. So I have to make sure that everybody writes here, and then once everybody has written here, I will ask the 0th warp to perform the sum. So that's essentially the algorithm. So once I do get every single of these data in the shared memory, I call sync threads, and then I ask 0th warp to compute a sum, and I'll get 55 back. And this is how the code looks like. So let's see. I'm specifying a shared memory here. So this is my shared memory. It's of size 32. I'm getting the ID of a thread in a warp. So my warp is 8 wide. I want to know which thread in this warp I am. Am I the 0th one, the first one, or the second one? Then I will call a function called warp reduce that will, there is a very fast way of computing this sum. Let's call it warp sum. It's just a Harvard thing. If you're interested, I can explain that. But let's call that warp sum. That given this 12 minus 1, 4, 5 will give me 31. So let me call that. Then if I'm the 0th lane, I will put that value in the shared memory. So I will write the partial sum in the shared memory. Then I wait for everybody to get there, so sync threads. Then if I'm the 0th warp, I will perform another warp reduce sum, and then I'm done. The only thing that you should take care of is that it's possible that some of these warps, you have less than 32 warps. So I make sure that if I have less than 32 warps, I set those values in the shared memory to be 0, so that I don't sum of garbage values. That's it. And that's warp reduce sum. There is shuffle instructions that you can do it very fast. And if you're interested, I can explain that later. Now, you see a lot of these like recursive algorithms, like reduction, and it's usually they use that kind of algorithm. And if you want to do a very big array, I can do another recursion. Ask every block to perform this partial sum, then again schedule another kernel to compute the partial sums of blocks. That's how you do the global reduction. And there is actually a library I think called COP that is an optimized library that does that for you. So there is a problem called shared memory bank conflict that you should be aware of. So the data in that shared memory is stored in a number of banks. So every bank, depending on the GPU, usually is 32-bit words. So if I have a float, the first float is 4 bytes, will live in bank 0. The second float will live in bank 1, etc. And so the problem is that this is a very fast shared memory. If you access the different banks, but if you access, everybody wants to access this bank 0, that's not fast. It will be serialized. So that's what's called as bank conflict. So let's say I'm one of the warps, and all of these threads in this warp will access different banks. This is fine. Very fast, usually within 1 to 2 cycles you will get the data. I don't have to access the 0th bank. I can access bank 1 if I'm 0. They can randomly access different banks. As long as no two threads access the same bank, there is no bank conflict. But I can have a two-way bank conflict where 0 and 1 are trying to get data from bank 0 or write data here. The hardware will serialize this. Will first honor the request by 0 and then 1. So this is a performance bottleneck. And I can have a worse bank conflict, 4-way bank conflict. This is a very important bottleneck that you have to be aware of. So this will be serialized.
Yeah, for this kind of conflict, typically how many cycles will it take?
It depends on the GPU, the architecture. I don't have a number for it, but it depends on also the number of way, like if it's a 4-way bank conflict or if it's an 8-way bank conflict. At most you can have like a 32 bank conflict if you have a warp size of 32. I guess it depends on the architecture, but I can look this up and then later post it in Piazza for like a typical GPU. But it's an important performance bottleneck. There used to be a problem with global memory bank conflicts. Right now, with new architecture, that's not the case anymore. I used to work on this at AMD, but newer architectures don't have this problem, so you don't have to worry about that anymore. But the important thing for global memory is coalescing memory. So let's say I have this matrix, very large matrix, let's say 4,000 by 4,000, and I can have different access patterns. I'm going to work on all of this matrix. I can work, row-wise, I can work column-wise, that's up to me. If I do it incorrectly, the performance will be terrible. Let's say this matrix was stored in row major, which means that when I run in the number of columns, these are contiguous in memory. If I access those, this is coalesced. What that means is that when a thread requests this data, the hardware will give you more data. So you requested this number. It won't just read, read a single float. It will read a page of memory, and it will bring it to your cache in the block. If I want to do executions like this, it will bring data that I'm not going to use. So this will be completely wasted. And I'm going to read byte by byte from the global memory. And as I said, GPUs are not really efficient when you're accessing global memory. They don't have the same hardware as in the CPU, so that's really not good. Even on the CPU, you shouldn't do that. So make sure that when you're writing code, you know how you wrote the data in the memory and try to use the same pattern, access pattern. And we'll see how this affects performance. So let's take a very important application, matrix transposes, which is the heart of FFT. If you see FFT numbers for every new architecture that comes in, it's essentially matrix transpose. So what we want to do is we want to read in A, and we want to store the transpose of A in B. So that's the formula. I'm going to put Aij to Bji. That's it. There is literally no computation involved, so there is no way that I can hide memory cache misses with anything. So I have to make sure that I do the right thing with the memory accesses. So let's take a look. Let me first transpose this. Let me read aij and write it in bji. What's the problem with this code to begin with? Will this code perform well?
For the access to A, it's relatively fast because all the data on that row is on the page. However, when writing back to B, you have to write like write to multiple pages, and the bandwidth is wasted.
Exactly. That's exactly the case. Do you have a solution to resolve this problem? Does anybody have an idea to like speed up this bottleneck? So let's first understand. So I'm reading A. This is no problem, contiguous in the memory, but I'm writing B completely incontiguous. So all of these, there is a jump. The next data is here. I'm jumping all the way, writing this, and all the way writing this. So is there a way to speed up this in a way that's more cache friendly or global memory friendly?
Blocking.
Yeah, exactly. You can block it. So you don't have to write all of this here in B. I can write a block of B. I can, let's say, transpose this part of A, put it back in this part. I can do a transpose in a block manner. So let's first look at the naive transpose. This is the code for naive transpose. I'm reading a constant float A and putting it in B. I get the x and y coordinates of this thread, where it is in the matrix. And I say, read A at x and y, put it in B. It's pretty clear code, right? Just read the x and y from A, put it back in B. Everything is behind the scene happens, but there is a problem of no global memory coalescing for B. And this is how I defined the grid. I said every block, let it be 32 by 32, 1,000 threads. So there's 1,000 threads that will read this part of A, and they will write in this part of B. Now let's do the blocking version. And I can actually use shared memory for blocking. So how does this work? I can read the right corner of A. Every thread will read it. It will put it in a shared memory called tile. Then I will write the transpose part of this tile back to the global memory. And this will be much better, because now I'm writing in B in a more or less coalesced fashion. So at least these parts are coalesced, and these are not. But it's better than putting one by one. And do we need any kind of synchronization here? Can I do it without synchronization? Yeah, exactly. You cannot do that. We have to first wait for all of the threads within a block to write their data into this tile. After everybody has written their data, then I can write this back to B. So that's essentially the, you have to wait. But there is a second performance problem here. Does anybody see what's the final performance problem here? Our accesses, go ahead.
If we can use two tiles, then upon the one tile is filled, then we can start writing that, and we can start reading from A for another tile. So that's like utilizing two tiles, one for reading and one for writing. Then, because upon the fill up of that tile, you have to wait until all the contents are dumped into B. Then you can start the next read from A.
I see. So you're saying before waiting for all of the second phase to finish, you can start doing it again.
Yeah, so it's like a buffer.
Sure, you can do that. Usually shared memory, you have very limited shared memory, but that's a possibility. But even with that algorithm, there's a problem.
I guess that's bank conflict.
Exactly, there is a bank conflict. So same way with the global memory, when I'm doing this, it's all accessing the same bank in the shared memory. So all of these are mapped to the same bank. And all of these writes back are going to be serialized. So this also doesn't perform well. How can I solve this there's a very elegant way of solving this. Does anybody have a guess for that? You know, one way would be to do a messy thing of, you know, let's say when I'm writing it here, write it in a way that they go to different banks, so that when I'm writing it back, I write first this guy, then this guy, then this guy, and this guy. So it kind of goes to the different banks. But there's an even much, much better way to do this. So did everybody understand how you can resolve it by writing it in different banks? But that's very messy. If I define my shared memory like this is very, every time I look at this, I really like this solution. Does this solve my problem? It's kind of non-trivial in the beginning. When I looked at it, I had to really think, why does this solve my problem? I'm not gonna do it myself, like writing it in different positions, but when I define my shared memory like this, what's gonna happen is that now there is a shift here. I don't have to see that shift, but the hardware sees it. So when I write this element, it actually doesn't go to the same bank. So I can simply just pad it with 1. And this was 32 elements. When I want to come here, this is not the, you know, if this was 0, 31, this is not 32. For hardware, this is actually 33. So it's not on the same bank. And if you do this, no more bank conflicts, and you will have a very, very good transpose. So this is the code. I'm defining my tile to be, you know, 32 by 32 plus 1. I get my x and y coordinates. I read A, put it back in tile, wait for everybody to put the results into tile, then just put the transpose of tile back in B. And this code will perform much, much faster than the original code. And this is a very interesting problem. There is a problem for in-place transposes. You know, you can think of, let's not waste memory, let's do an in-place transpose. If it's a square matrix, it's pretty easy. It turns out that if you have a rectangular matrix, performing transpose is very, very tricky, both for the CPU and the GPU. And this is a very, very non-trivial research problem. And in 2014, there were 2 papers that came, I think, in PPOP. Here it says SIGPlan notices, I think this was in PPOP. And one was from Wenmei Hu in UIUC. So same conference, same committee, 2 different methods. And the next one was from Brian Catanzaro, a graduate of Berkeley, who was at NVIDIA Research at the time. 2 different methods for a problem that's very, very hard to get performance, and still, these get state-of-the-art performance, but it's far away from peak. So if you're interested to work on a problem, this is a very good, if you can get something out of it, it's very important to get this thing fast. So this was Brian's solution, where he does a very, very elegant approach to solving this problem. All right, so there's other features available on GPU that you may want to be aware of. There is support for, you know, atomics. You know, you have signed power functions, ATAN, CU, etc. There you have atomics as well, and you know, in general, it's best to avoid atomics, but you may have an application that you cannot avoid it, and that's available for you. The CUDA runtime supports for you, gives you CUDA malloc. If you want to allocate something on the GPU, if you allocate too much, it returns an error. It tells you CUDA malloc failed. Same way as malloc. And you have to make sure that you free. This is very important. You make sure when you do malloc, make sure there is a corresponding free. There is memcopy, similar to, you know, the usual CPU memcopy. There is texture, and there is a lot of things for graphics. So there is a bunch of very cool hardware accelerated things here for the graphics part. There was a paper I read like 2 years ago where they used texture to do cubic interpolation. So cubic interpolation is very, very notorious to get good performance out of it. But the GPU has hardware accelerated linear interpolation because they were doing graphics. So there was hardware things for doing linear interpolation. And so there was this guy who looked at this and wrote a cubic interpolation as a bunch of linear interpolations and got peak performance out of the GPU. So maybe if you got some time, take a look at things that are supported here. You can use it for your application and get really, really good performance. Then we have the OpenCL. So first there was CUDA, then about a year after, there was OpenCL. So there is 2 major companies that make GPUs. There is NVIDIA and there is AMD. And for AMD, you have to write in OpenCL. So in OpenCL, it's pretty much the same way as writing a CUDA code, except that it's different names, I would say, and a little bit longer. But the good thing about OpenCL is that you can run it on different architectures. So you can run the same OpenCL code on an NVIDIA GPU as well, and that's supported. And so Apple, I think, there's Apple, Qualcomm, and a bunch of companies, and I think it's Kronos Group that is maintaining OpenCL, if I'm not mistaken. So very similar concepts, unfortunately different notation. It's really unfortunate that there is this thing, but the concepts are all the same. So the thread here in OpenCL is work item, just different name. If you have shared memory, it's called local. If you want to define like the tile, you have to prepend it with local. Then the kernel, instead of global, you should say kernel. But the concept is exactly the same. And if you're interested, there's a very good course that Wenmei Hu at UIUC has on Coursera, and he has a book that I read that is a very clear explanation of how to go from CUDA to OpenCL. So essentially, if I want to summarize again, you have thousands and thousands of threads that you should, it's your responsibility to utilize them effectively. There is on-chip memory, shared memory that's much faster to access. Try to avoid global memory accesses with, or try to coalesce it with contiguous memory accesses or hide it with computations. On NVIDIA GPU, this Siamese twins size is 32. So every 32 threads live together. They have to execute the same instructions and try to avoid memory divergence, essentially. There's a very, very, very good tools for profiling the code, and this is really helpful if you want to see where is your performance bottleneck. You look at the code, you don't know whether it's cache misses or global memory coalescing. You can use these profilers both for AMD and NVIDIA have it. For CUDA, you just say CUDA profile code 1. It runs your code a couple times, and it gives you really good suggestions. So it gives you both the timings for each kernel, and it gives you suggestions of what's going wrong with the code and how you can increase the performance. So in summary, the algorithm that you have, if you want to run it on a GPU, should have a lot of parallelism. And so you see people comparing things that are not really built for GPU, and they say GPU is very slow. Well, they were not designed for that algorithm. So you see that a lot these days. And in short, there is good locality. It's very, very crucial because there is really no intention of, it's hard to solve this. It's a very, very large die, and you cannot really put everything there. You cannot have a very expensive cache hierarchy to so many ALEs. So it's your responsibility to make sure that that's taken care of. And global memory used to be a big pain with the global memory bank conflict. That's almost resolved right now. And you have to just make sure that the access pattern is optimal. So if you're doing matrix multiplication, make sure that you're doing it in a way that's, for example, blocked, or in a way that you have maximum coalescing as possible. And then shared memory bank conflicts, try to do add +1. There is sometimes there's a problem with that because when you request more shared memory, it reduces the occupancy in the GPU. So if you can try to avoid it with different methods, that would be better actually. And if possible, avoid thread divergence, even if that means that using an algorithm, that's not necessarily optimal. So where do you go from here? There was a lot of information. Hopefully some of it was useful. But if you're writing an algorithm that uses a lot of matrix multiplication and different things, you don't have to write your own matrix multiplication. There's libraries for this that have been optimized really, really well. For example, cuBLAS is the same operations supported by BLAS are there in cuBLAS. Very similar interface. There's cuSparse for performing sparse multiplications, which is very hard to optimize for GPUs. There's COFT for performing FFT, etc. And I suggest don't necessarily start with these. Maybe write your code and compare your performance with these as a benchmark, so you know how to optimize the code. Because in future, I think you will be asked, if you work for a company, to write a kernel that's not supported by GPU, and you need to figure out what was wrong with your code. Here, you can actually compare with the cuBLAS code and see the tricks that were used there. Then there is a very interesting, if you're looking for project ideas, there is very interesting opportunities for multi-GPU programming. So here, that link between a CPU and GPU becomes a bottleneck. Really, the computation, everything that we talked about, that won't be the bottleneck. And how to make sure that that communication time, that talking in the PCIe is minimized, there's a lot of really interesting open problems there. And there's two classes for that. Either you have GPUs that are directly connected with the PCIe, they share the same CPU. NVIDIA provides unified memory where it's completely transparent to you. You just access a device, and the NVIDIA makes sure that that pointer is copied to this GPU. And there is distributed memory multi-GPU programming where you do message passing. You essentially do hybrid message passing interface plus CUDA. Is MPI covered in the class? It's covered already? Okay. So it's essentially hybrid MPI plus CUDA. Really good research problems here as well. And the next level is writing code in assembly. This may seem a little bit a daunting task, but there is actually a good post by Scott Gray that he says, he walks you through how to write an assembly code for cuBLAS. And I highly encourage you to read that blog post on GitHub. I can send the link. It really exposes to you a lot of things that if you want to get really good performance out of a GPU, you should know. How to, like the whole pipeline of what happens when you read data from global memory all the way to this register before doing these additions. How can you reduce these overheads? It's a very detailed post, and he was able to get 4% better performance than cuBLAS, and 4% may seem not a large number, but it's pretty large given that a lot of people had worked on cuBLAS. The problem is that NVIDIA and AMD don't give you their assembler for good reasons. So you cannot actually write a code in assembly and compile it, but there is an open source assembler for Pascal and Volta, Pascal and Maxwell, that you can use. And the trick there is to compile a code already in CUDA, then look at the assembly and inject your code there. So you don't have to write everything from beginning. You compile a simple code, and then you start by modifying assembly code there. And the gains are enormous. So if you really are interested to becoming a GPU guru, I highly encourage you to take a look there. Now, if you want to take other projects, I highly recommend this book by Wenmei Hu. It's a really good book, Programming for Massively Parallel Processes. It has new chapters on machine learning and how those kernels are optimized on GPU. And there's a very good paper by one of James' students benchmarking GPUs to tune dense linear algebra. That's a very good article, and it actually got the best paper award, I think. And if you want to do, for example, BLAS optimization for your project, I encourage you to start with this. And I think they were able to beat the then NVIDIA's performance by a much larger margin than 4%. I think like maybe 50% better. It was a very interesting paper. I think it has like 800 citations or something. So these are the two references that I recommend. I used slides from Brian Catanzaro, who was a PhD student here. He's now a VP of Applied Deep Learning at NVIDIA. Also, John Owens, who slides for him from last year, and Professor Keshav Bengali, that I took his course at UT Austin as a grad student. And Parallel for All is a very good blog post there. I used a lot of material there as well. So feel free to contact me if there was any questions, or if there was anything unclear, or if you're looking for research ideas. There is a couple of things for that you may be able to beat the library's performances. So if you're interested, feel free to email me. And again, many thanks for having me here.
All right, so just a reminder that homework 1 has been extended to February 13th because of the downtime for Corey. So that's now due on the 13th. You have a couple more office hours to get in your in-person questions, and you can always crowdsource it on Piazza. All right, thanks.